Welcome back to the Deep Dive.
So we're all moving past the initial hype of large language models, and we're getting right into what I think is the core engineering challenge of the moment, which is the rise, and let's be honest, often the frustration of the LLM agent.
Oh, absolutely. We're talking about those autonomous systems that we're trying to task with, well, everything. Generating complex code, multi-step web research, you name it.
And if you, our listener, have ever tried to actually build one of these things for a real-world task, you know the two major hurdles. I mean, they just smash right into your productivity.
The first one is just the sheer effort of configuration. It's this tedious manual prompt engineering, the endless, crafting of tools, the struggle to get the agent to just reliably follow a plan.
It really does feel like you're a 19th century craftsman, right? Like you're forging every single bolt by hand. Exactly. And that leads you straight into the second problem. The moment you finally deploy that agent, it's static. It's fixed. It doesn't learn. It won't adapt to a new environment. It can't learn from its mistakes. And it gets obsolete so fast because the world, the APIs, the task itself, it all just shifts.
That static nature, it just cripples any real attempt at scale.
And those twin bottlenecks, the high cost of configuration and these static capabilities, that is exactly what the Tencent Youtu Lab set out to solve with their framework, Youtu-Agent.
So that's our mission for this deep dive. We're going into this paper to really understand how they engineered a unified system that handles the entire life cycle of an agent.
From its automated construction from the ground up right through to this continuous, almost self-guided evolution.
And I want to be clear, this isn't just another small iteration on the frameworks we already have. It feels like a foundational rethink.
It is. The big picture here is that Youtu-Agent brings this really robust dual solution to the table.
Okay, so on one side, you have these sophisticated generation mechanisms. They automate the whole agent construction process. You just described the goal.
And the system just goes. It designs the blueprint, it writes the necessary tools, configures the whole environment, all autonomously.
And then on the other side,
you have the hybrid policy optimization system. This is the continuous evolution part. And they give you two distinct paths. One for low-cost, quick improvements, and another for, the heavy-duty reinforcement learning.
So the agent can just perpetually get better. It learns from every success and failure it sees in the wild.
Right.
And to really ground this, to show why this is so revolutionary, let's just hit you with a quick win teaser right up front. When we talk about improving a powerful agent, we're usually talking about deep reinforcement learning, fine-tuning, and costs in the tens of thousands of dollars.
And weeks of training time.
Exactly.
Yeah.
But Youtu-Agent has this low-cost learning mechanism they call agent practice. And through this method, they got significant performance gains.
And not just marginal gains. A robust plus 5.4% improvement on the AME 2025 mathematical reasoning benchmarks. That's a really competitive space.
Okay, but here is the shocker. This level of improvement was achieved with only 100 training samples and a cost of approximately $18.
18, and this is the key.
Yeah.
It required 0 gradient updates. It never touched the model's core weights, which is an absolute game changer. I mean, you contrast that with the traditional RL methods. You're looking at maybe 10,000 samples, $10,000 or more to fine-tune a big model.
It means that continuous evolution is no longer locked behind a massive compute budget. It suddenly becomes accessible.
It really does.
Okay, let's unpack this then. Before we get into that incredible cost-saving part, we need to understand the foundation. How can an LLM reliably build and improve a system if it's not structured properly?
That's the right question to ask. So that brings us to section 1, the modular foundation. It's all about decoupling the agent stack. They really saw that complexity demands, simplicity in architecture. Absolutely. Yeah. The entire architecture is built on a modular 3-layered execution framework. And it's designed specifically to decouple all the different concerns.
So you're separating the environment, the tools, the agent's actual logic.
Right. And by doing that, you maximize flexibility, you can reuse components, and most importantly, you provide a standardized target for their automated generation system to aim at.
So let's walk through those layers, starting from the bottom. What is the environment layer?
So the environment layer is the foundational context. It's the substrate where the agent actually acts. It provides all the primitive interfaces that expose the state of the world to the agent.
Okay, so give us some examples. What does that look like in practice?
Sure. This could be a browser instance, based on something like Playwright for web navigation. Or it could be an OS shell for running system commands. Or, and this is very common, it could be a sandboxed code execution environment, something like E2B for doing computational tasks safely.
So it's not just the external world itself, but the standardized interface to interact with that world.
Precisely. The critical design choice here is abstraction. If you standardize that interface, the same high-level agent, the same tools, they can all operate across totally different backends.
So a browser, a Linux shell, a coding sandbox.
Right. With minimal or even zero changes to the core logic. It just defines where the action happens and how you observe the results.
That makes a lot of sense. So if the environment is the operating theater, then the tools layer has to be the specialized instruments, the scalpels and clamps.
That's a perfect metaphor. The tools layer is where you encapsulate all the operations, both atomic and composite ones. You present them as these stable, documented interfaces the LLM can call.
And they break these tools down into 3 categories, right? For clarity.
Right. They do. The first one is the environment-related tools. These are just direct wrappers around the low-level APIs from the environment layer.
So for a browser, that would be something like clickdom element.
Exactly, or type text. They're stateful, they depend on the environment's context. The second group is the environment-independent utilities.
Okay, so these are standalone.
Totally standalone. Think of a complex math function or a datetime formatter. Their output only depends on their input, so they're super robust and reusable. And that brings us to the third, and I think the most interesting category, the MCP tools. The Model Context Protocol. What is the real significance of this? This isn't just some fancy name. The MCP is the standard communication pipeline for integrating external services. Or, and this is the really crucial part, for integrating the newly synthesized tools.
Ah, okay. So if the system generates a new tool on the fly.
The MCP is how it gets plugged in seamlessly. Imagine you need to integrate a private corporate API or a specialized machine learning service. The MCP is the standardized way to expose that complexity to the agent with just a simple function signature and a clear docstring.
So it guarantees that no matter how complex a tool is or where it came from, the agent layer just sees a uniform, predictable interface.
That's the key to scalability. Once a tool is defined or synthesized, it's instantly portable.
Okay, so that brings us to the brain of the operation, the agent layer. This is the LLM planner, the executor, using that standard perceive reason act loop. But inside this brain, there's a vital organ called the context manager.
Yes, and this module tackles one of the most brutal real-world challenges for any agent, which is just maintaining focus over a long task.
Right, the long horizon problem. The context window just gets flooded. If you're doing web research, every step returns hundreds of lines of HTML.
It's like trying to think while someone is just shouting old, stale information at you. You lose the plot because your working memory is completely overloaded.
So the context manager is the filter.
It's a very sophisticated filter. It's designed to handle this trade-off between, preservation and pruning. It actively prunes stale or redundant info like the raw HTML from a page you've already successfully navigated,
while preserving the essential stuff, the state variables, key findings.
Exactly. But here's the critical question. How do you know the LLM is pruning the right stuff? Isn't there a huge risk of it just, forgetting step 1 when you're on step 10 just to save tokens? That is the fundamental challenge, and they address it by making the pruning logic configurable and task-aware. Often, it uses structured summarization or key value tracking, which is still driven by the LLM, but managed by this external module.
So it's enforcing a compact working context.
Right. It slashes the token cost, which is great for affordability, but more importantly, it prevents that catastrophic performance drop you get from context window overwhelm, that lost in the middle problem.
Okay, so it's a disciplined, curated memory system.
Yeah.
So how do all these pieces, the environment, tools, context manager, how do they all get put together? That's the YAML configuration, right?
This is the glue. This is what makes the automation possible. Every single element from the environment you choose, like E2B, to the tools you select, like Search and Python Executor, is all defined in a human-readable YAML file.
And the beauty of YAML is its clarity.
It is. And that clarity serves 2 massive purposes. First, for a human developer, it turns agent definition from a messy pile of hard-coded prompt strings into a systematic, version-controllable structure.
Which is huge for team collaboration and just deploying this stuff in the real world.
Huge. But the second, and for this paper the most critical purpose, is that this standardized structure provides the precise target schema for the automated generation. The LLM doesn't have to guess how to build an agent.
It knows it just needs to output a YAML file that follows this specific architecture.
Exactly, and we can see it in the example snippet they provided. It's so clear. It defines the agent name, gives the high-level instructions. Then under config, it just lists everything out. The N is E to B, the context manager is base, and it defines the toolkits. It's declarative. You just tell the system what you want, what resources it has, and the modular system handles the rest. And that declarative structure is the entire reason the next section, automated generation, actually works, which is a perfect transition into section 2, solving high configuration costs. We've established that the manual craftsman approach is just too expensive and slow. Youtu-Agent throws that out for 2 complementary generation paradigms. They recognize that not all agent-building tasks are the same. If you have a well-defined routine task, you want speed and reliability.
But if you have something ambiguous or complex, you need flexibility and dynamic reasoning.
Exactly. Hence the workflow mode and the meta-agent mode.
Let's start with the workflow mode. This is the deterministic 4-stage pipeline. It sounds like the factory assembly line for agents.
It really is. It's built for guaranteed structural validity and speed. So stage 1 is intent clarification and decomposition. The system takes your high-level, request-like, scrape stock data from NASDAQ and breaks it down into technical requirements.
So it identifies the objectives, capabilities, constraints.
Right,
resulting in a highly structured specification. Then you get to stage 2. Tool retrieval or ad hoc tool synthesis. Okay, this is where the magic starts.
It is. The system first checks its library for existing tools. If something's missing, the LLM activates this ad hoc tool synthesis submodule, and this isn't just generating some pseudocode.
It's generating actual functional Python code.
Functional Python tool implementations, complete with function signatures, clear doc strings, and even basic unit tests to make sure it actually runs.
Hang on, an LLM generating unit-tested, executable Python code from a high-level requirement, which then becomes a reusable tool. I mean, that capability alone is revolutionary. The tool library just grows itself.
Precisely. It turns tool creation from a manual chore into an autonomous capability. Then, stage 3 is prompt engineering. With the tools selected or just created, the system generates the optimized system instructions.
So the prompt is perfectly tailored to the tools it was just given,
which maximizes efficiency and cuts down on hallucination. And finally, stage 4 is configuration assembly. Everything, the environment, the tools, the prompt gets compiled into that final, ready-to-deploy YAML file.
That's a really powerful, self-contained system. But like you said, not all requirements are so neat. What happens when the user's request is fuzzy? That's where the meta-agent mode comes in, the dynamic architect.
This mode is for the complex, ambiguous stuff that a fixed pipeline just can't predict. Here, a higher-level architect agent is created. And instead of just following those 4 stages, this meta-agent treats the generation capabilities themselves as tools.
So the meta-agent is like a project manager. Its job is to understand the requirement, find or build the resources, and then assemble the final product. What tools does this project manager have?
It's got its own special toolkit. First, a search tool to find existing tools in the library. Second, a create tool module, which is that synthesis engine we just talked about.
Okay.
Third, and this is the game changer for ambiguity, is a scuser. This facilitates a multi-turn dialogue with the human to clarify what they want. It avoids building the wrong thing based on a bad assumption. And fourth, create agent config, the final assembly tool.
That scuser tool fundamentally changes the whole interaction. It's not a rigid command anymore. It's a collaborative design process.
Yeah.
So looking at the metrics, how do these 2 modes actually perform?
The results were really validating. On configuration validity, basically, did it output a structurally sound YAML file? The deterministic workflow mode hit a perfect 100%. The meta agent was at 98.75%.
So they're both highly reliable just building the configuration.
Very, but the real challenge is synthesizing executable code, the tool executability rate, the TE rate.
Right. How often did it successfully generate runnable Python code?
It was over 81% for both modes. 81.25% for workflow, 82.50% for meta agent. Just think about that for a second. 4 to 5 times it needed a new capability, it just wrote it successfully.
That's a massive reduction in human effort. That's how you lower the configuration costs. And in terms of actually solving the task, the meta agent was a little better.
Slightly. Task completion was 68.75% for the meta agent versus 65% for the workflow. And that little edge confirms that for diverse, complex tasks, that dynamic planning and user clarification, it really pays off. Okay, to really appreciate this, we have to walk through that case study, the user query. Summarize today's trending papers on multi-agent system and download PDFs. That's research, web interaction, file management. It's a classic complex task. So the meta agent kicks in, it defines the requirements, Find papers, summarize them, download the files. First, the architect agent calls the search tool.
And finds an existing ArcSift toolkit. Okay, step 1 is a success.
Right. But then the agent notices a gap. The existing tool is generic. It doesn't have a specific function for fetching daily trending papers, so it needs to synthesize a new capability.
So it calls create tool.
Exactly. A subagent gets to work. It doesn't guess. It searches online for API docs, common libraries for getting that trending data. It then implements the Python function, say, fetch daily papers.
And this new tool is validated and then plugged in using the MCP.
Perfectly integrated. Finally, the agent calls create agent config to assemble the YAML. The final agent now has the search toolkit, the ArcSift toolkit, and the brand new functioning fetch daily papers tool.
So the process isn't just assembly, it's self-improvement and custom fabrication in real time. The agent found a gap, wrote the code to fill it, and integrated it, all without the user writing a single line of Python.
That's it. The developer's role shifts. You go from spending 80% of your time on boilerplate setup to spending 80% of your time defining high-level goals and just reviewing the autonomous solutions. Okay, so that eliminates the high configuration cost problem. Let's pivot now to the second major problem, static capability. How do we keep the agent sharp once it's built? This brings us to section 3 and the low-cost path. Agent practice. This is where we get that incredible $18 result. This module is really the accessible antidote to the traditional problem. Manual prompt optimization is a nightmare, and traditional SFT or RL is just prohibitively expensive. Agent practice offers a novel, low-cost way for the agent to evolve during runtime.
And it does it without any parameter updates or gradient computation.
Oh, not at all.
And the technique is called training-free group relative policy optimization, or GRPO. That sounds technical. If it's training-free, how does it actually let the agent evolve?
It basically leverages the LLM's own powerful reasoning and comparison abilities as the learning engine itself. So think of it less like training a model and more like giving a very smart student a study guide that's derived from their own best and worst performances.
A study guide. I like that analogy. So walk us through how this study guide gets generated.
Okay, so the process starts with parallel rollouts. For a given task, like a complex math problem, the agent runs the task multiple times in parallel on a small data set. This generates a bunch of different solution paths.
Some successful, some failures.
Right, so you have a stack of A papers and a stack of F papers for the same test. Next comes LLM evaluation and distillation. A different LLM, acting as a high-level evaluator, assesses the relative quality of all those trajectories.
And it's not just scoring them, it's reasoning about why one path worked and the other didn't.
That's the key, which leads to the semantic group advantage. In normal RL, you'd calculate a numerical reward. Here, they distill a semantic advantage, a textual learning direction.
So it's a natural language summary.
It's a summary of the experiential knowledge. For example, it might conclude, when you see an algebraic expression, always check the boundary conditions before using the solver tool, because we saw that you failed when you rushed to use the tool first.
It's like generating a set of polished, expert-level heuristics.
Perfectly put. And these heuristics get accumulated. This refined knowledge, the study guide, is then injected into the agent's context during future tasks. And this injection acts as a set of optimized instructions. They call it a textual LoRa.
Ah, the textual LoRa. That's a crucial concept. So for our listeners, LoRa is a method to efficiently fine-tune a model's weights. This is doing the same job of guiding the policy, but it's doing it purely inside the context window.
Without ever touching the model weights. Which means you can use this method even with black box models you can only access via an API where fine-tuning is impossible. It just instantly updates the agent's performance by refining its working memory.
And the results on the AIME math benchmarks are the ultimate validation of this.
They're undeniable. On the AM 2024 benchmark, the practice module got a plus 2.7% gain in accuracy. On the much harder AM 2025 benchmark, it jumped by a remarkable plus 5.4%.
We have to linger on the cost comparison because this is the headline.
It really is.
Traditional methods for these kinds of gains, they cost over $10,000.
And Youtu-Agent achieved this up to a plus 5.4% improvement with only 100 training samples and about $18 in learning costs. It's disruptive. It removes the economic barrier for small teams, for individual developers who need their agents to keep getting better.
And there's another fascinating finding in their data in Figure 5. As the performance goes up across epochs, the average number of tool calls actually decreases. What does that tell us?
It tells us the agent is learning true efficiency. If it were just getting better by brute force, you'd expect tool calls to stay the same or maybe even go up. The fact that they decrease means that semantic knowledge, the textual ORI, is guiding the agent to skip unnecessary steps. It's learning more strategic, more precise problem-solving paths. It's actually getting smarter, not just trying harder.
So agent practice is this fantastic solution for continuous, cost-effective improvement.
Yeah.
But what if you're building an industrial system and you need the absolute maximum performance? You need to fundamentally change the model's behavior.
Right. That brings us to Section 4, Continuous Optimization Part 2, the Scalable and Stable Agent RL module.
Exactly.
For industrial scale, you do need to update the core policy, adjust the model parameters through end-to-end reinforcement learning. But Agent RL has historically been plagued by two massive problems, the twin challenges, scalability and stability. Let's talk scalability first. Why is it so much harder to scale RL for agents? It's because they're stateful. Agents interact with environments sequentially. If one worker in your distributed setup fails or times out, the entire batch of experience data can get corrupted. Standard distributed training just breaks down.
And Youtu-Agent engineered solutions for this, getting a 40% speed up in training time compared to the official Agent Lightning framework. How did they pull that off?
They implemented a whole suite of solutions designed for massive parallelization, scaling up to 128 GPUs. First, RESTful API wrapping. They encapsulated the agent environments as standardized services using RESTful APIs.
So the training pipeline doesn't need to know the internal specifics of a browser instance.
It just sends a standard request and gets a standard response. That's crucial for distribution. Second, they used Ray, the distributed computing framework, for highly parallel rollout collection.
To speed up the data generation bottleneck.
Right. And third, layered timeout logic. They added timeout controls at the tool, step, and episode levels. So if a single tool call hangs, which happens all the time with web stuff, it doesn't crash the entire training run.
That reliability is what enables the scaling. And a 40% speed up is just transformative for the economics of this stuff. But speed is nothing if the policy degenerates, which is the stability challenge.
Ah, yes, the entropy explosion. This is when the agent's learned policy just becomes chaotic. It learns to spam the same tool, make nonsensical API calls, get stuck in loops.
So how do they stop the policy from, losing its mind?
They applied very targeted fixes to the core RL algorithms. First, they filtered invalid or anomalous tool calls right away. If the agent does something nonsensical, that experience is flagged and filtered out so it doesn't learn bad habits.
Okay.
Second, they addressed data overfitting. They actually removed batch shuffling and reduced the number of off-policy updates. This makes sure the policy learns smoothly from the flow of experience, not chaotically from randomly ordered stale memories.
And third was bias correction.
Right. They corrected for bias and the advantage estimation to make sure the learning signal was accurate and stable, which prevents volatility.
And you can see the results visually in their training curves. The baseline has these abrupt spikes in the PPO-KL divergence, but their system is just smooth.
Exactly. Think of the KL divergence as the agent's panic button. If it spikes, the policy is taking a massive, unpredictable leap. Youtu-Agent system keeps that stable, it controls the gradient norm, and you see this steady, consistent increase in accuracy. They made a fragile process reliable.
So what did this stable RL process actually deliver in performance? They used the Quint 2.57b model for these tests.
The gains were massive. For math and code tasks, the model's accuracy on the AME 2024 benchmark surged from a baseline of 10% all the way up to 45%. That's a plus 35% raw accuracy gain.
35%. That is staggering.
It is. And on search tasks, using a local Wikipedia tool, they saw deep improvements across the board. Natural questions accuracy went up by 21%, PopQA up by 19%, and HotPot QA, which is really tough multi-hop reasoning, improved by 17%.
So this RL module provides the pathway for engineers who need to absolutely maximize an agent's performance ceiling.
The message is that you're no longer trapped. You have two distinct choices for continuous evolution now: the fast, cheap, in-context agent practice, or the high-performance parameter updating agent RL module. Either way, you get evolution, not stagnation. Okay, let's move into Section 5, validation and application. The framework is great in theory, but it has to deliver on standard benchmarks, and it does. And what's key is that it's achieving these results using entirely open-source models, mostly the DeepSeek series, which shows how generalizable it is.
So let's hit a couple of highlights. First, WebWalker QA.
This is a tough one. It tests multi-step, deep web navigation, clicking links, filling forms, answering questions from multiple real websites. Youtu-Agent achieved 71.47% pass at 1 accuracy. That really validates the architecture and the context manager.
And the second is the GAIA benchmark, the General AI Assistant Test.
Right, the text-only subset. This mimics complex real-world tasks, and the framework achieved 72.8% pass at 1 accuracy. This high score just confirms that its tool selection and its ability to use those synthesized tools really translates into superior performance.
It's important to quickly put this in context with other frameworks people might know, like MetaGPT or AutoGen. Where does Youtu-Agent fit in?
Well, MetaGPT and AutoGen are fantastic at orchestrating agents with predefined static roles, but Youtu-Agent's key distinction is in 2 areas. First, it focuses on the self-generation of executable tool code.
It built its own parts.
Right. And second, it provides that unified pipeline covering the whole life cycle from automated generation right through to the hybrid optimization. It's the full package for a single agent's life.
Okay, that integration is definitely the differentiator. Now let's bring all this engineering complexity back to the end user. Let's talk about TIP, the on-device multimodal desktop assistant.
TIP is the realization of all this potential in a secure, accessible format. It's designed specifically as an on-device assistant, and that focus on running local models is key. It ensures data privacy and security, which is critical for real adoption.
So it brings the power of the automated agent right to your screen, but with a huge emphasis on privacy and user control. How does it integrate the Youtu-Agent framework?
In 3 core ways. First, it can just load and run existing Youtu-Agent YAML configs directly. So an agent you've configured for file management or some internal tool can just run inside TIP's UI.
Okay.
Second, it does proactive intent and context completion. TIP is always observing your screen context. If you highlight a dense legal paragraph, it doesn't wait for you. It proactively suggests things like summarize this or extract key entities.
That removes so much friction, no more manual copy pasting.
Exactly. And third is its GUI agent capability and what they call skills. TIP can automate desktop actions end to end. It can watch you do something like fill out an expense report by simulating mouse clicks and keyboard inputs.
And this ties back to the optimization modules. The system can save and replay those completed action sequences as reusable GUI skills.
Precisely. And that skill becomes a codified workflow that is now subject to continuous improvement. If an agent fails to book a flight 10% of the time, that faulty skill is captured, analyzed by agent practice, and refined with new instructions, making it more robust for the next time.
It turns fragile automation scripts into continuously hardening assets.
It does, and that demonstration they showed with the multimodal context is a fantastic example. You select an area of your screen with a picture of an ancient bronze vessel.
And TIP just figures it out?
It detects the image and text and proactively offers suggestions like explain bronze patterns or research historical period. It brings the power of this incredibly complex agent framework to the user just by letting them point at their screen.
It's a really elegant way to take deep research and deliver it to the end user in a secure, intuitive, and continuously improving package. So we have covered the full spectrum of the Youtu-Agent framework. Before we wrap up, let's just quickly consolidate the key takeaways.
Okay, first and foremost, the core architecture. That modular, stack decoupling environments, tools, and context management with the YAML system. It makes agents predictable and shareable. Second, the solution to the high-cost barrier. That dual paradigm automated generation. The workflow mode and the meta-agent mode achieving over 81% success in synthesizing new tools. Third, the breakthrough and accessible improvement. The agent practice module. That training-free GRPO mechanism getting huge performance jumps like that plus 5.4% on AIM for just $18 by using that textual ref. And fourth, the industrial grade path, the scalable and stable agent RL module, solving the bottlenecks of scalability and stability to get those massive lasting parameter improvements like the 35% gain on AIM. The core finding is pretty definitive. Agents just don't have to be static anymore. There are now guaranteed viable pathways, either low cost or high performance, to make sure they continuously improve, lowering the barrier to entry while raising the ceiling of capability.
Which brings us to the provocative thought we want to leave you with. Youtu-Agent has solved the problem of building agents and the problem of improving agents autonomously. But what happens when the next step is realized? When these self-improving, automatically generated agents start optimizing not just their own tool usage, but the internal architectures and the training pipelines of each other?
If we enable true multi-agent collaboration, where these self-optimizing agents are dynamically designing better blueprints for their peers and learning from a collective experience pool at machine speed, the challenge shifts entirely.
The speed of evolution could become difficult to even track, let alone manage.
The future problem won't be building one good agent. It will be architecting and managing an accelerating, complex evolutionary ecosystem of them.
The engineer's job shifts from builder to ecosystem manager. A fascinating challenge to consider as this technology matures. Thank you for joining us on this deep dive into Youtu-Agent. We hope you feel thoroughly informed and prepared for the age of the auto-evolving agent. We'll see you next time.